Okay, the next topic we have today is Pascal's principle. Pascal's the same Blaise Pascal who came up with the famous triangle that we use in scholastic bowl. Pressure is defined as force over area, so the label for that is Newton per square meters, and is measured in pascals named after him. Hydraulics is where we use the Pascal's principle for in a very useful way. Hydraulics is the use of non-compressible liquids in order to distribute pressure. Water is non-compressible, and the synthetic oils or the regular oils that we use for hydraulic systems are non-compressible. And that's key to understanding this. Now there's a series of derivations I'm going to make here. I don't expect you to know them, but I want you to see where it came from. So this is something that magical that Pascal came up with. Pressure is defined as force over area. We've discussed before, or here, that and other places, that density is mass over volume. Therefore, mass is equal to density times volume. We know that weight is mass times gravitation acceleration, and volume is height times area, area times height. So we put all this together. We know since that force is equal to density, which is mass times volume times gravitational acceleration, then we are going to have density times, isn't that magic? Wasn't that wonderful? Let's bring that back here. Thank you very much. Density times gravitational acceleration, and volume, as we said here, is height times acceleration. Now, we're going to divide by that area, and we have F over A now is equal to dGH, and F over A is, as we just said over here, is pressure. Now, the density of water and the gravitational acceleration are constants. Say, well, why is gravity constant? Well, the places that we're going to do this on, at least in the most of the Earth, in fact, almost all of the Earth, is not going to have a dramatic change from the acceleration being 9.80 meters per second squared. So we are considering that constant. Okay? And therefore, the height is going to be equal to the pressure times the constant. So since these are constants, then pressure is going to be proportional to the height. So, which is what, this is a proportionality statement, and this is the mathematical statement with the constant and replacing the proportionality symbol. Okay? Now, here's how we use that. Suppose you're diving 10 meters below the surface of water. If you're diving, hopefully not diving in the air. Creates what pressure on you by the water and by the combined with the atmosphere. So that's our first problem. So we're using P equals dGH, and G is 9.80 meters per second squared, and the height difference, the change in height, is 10 meters. So you're going from this point to this point down. So it's basically a change in pressure, but we're going to include all pressures here, as you'll see. Density of water is 1 gram per, not liter, that should be milliliter. So get that correct in there. And it's also in units of SI for mass and volume, kilogram, 1,000 kilograms per cubic meter. So the pressure of the water, according to the formula, D is 1,000 kilograms per cubic meter, G is 9.80 meters per second squared, and height is 10. I keep doing that. I love doing that. Okay? Multiply all that together, we get 9.80 times 10 to the 4th pascals, and we tend to measure atmospheric pressure in kilopascals, so that's 98.0 kilopascals. The total pressure then that is being exerted on you underwater is that 98 additional in the water plus 1 atmosphere of pressure, which is 100 kilopascals. Used to be 101.3, and they thought that was just nonsense. Let's just round off to 100, it's close enough. So that's approximately 198 kilopascals that you're feeling. So in other words, double the pressure than you were before you dove in. Okay? That's just 10 meters, that's 30 feet down. And that's doubling the pressure. Now, this is Pascal's principle. In non-compressible liquids, pressure is distributed equally throughout the liquid. This is really important in hydraulics. So P1 equals P2, which is F1 over A1 equals F2 over A2. That is the definition of Pascal's principle. Okay? Another example, a 55 kilogram gymnast is performing a single handstand. If her hand has an area of 20 square centimeters and the floor has an area of 120 square meters, what is the pressure at the point of contact and after the entire floor has absorbed the impact? Okay, so that's two different things. So as soon as she gets the hand on there, she's applying pressure to that particular specific area, but the floor has a give to it, much like a basketball floor, in which it absorbs it and basically spreads out the pressure throughout the system. So the area changes. So let's just look at the gymnast herself. Pressure equals force over area. Her force is her weight. That's 539 newtons. Her area is the 20 square centimeters, but we have to use square meters because SI is in square meters for area. So notice I have 1 meter per 100 centimeters, but they have to both be squared in order to be equal. So we can cancel out the square centimeters here. We have 2 times 10 to the negative 3 square meters. The pressure at impact is her weight, force, divided by the area of her hand. That, and we get 2.70 times 10 to the 5th pascals, or 270 kilopascals, about 3 times the pressure, or 3 times the force, or air pressure that is being dealt to the floor before she makes that impact. Now, we go to the pressure throughout the entire floor, and with that give, we have the force is her weight still 539, but now the entire floor is absorbing this, and that's 120 square meters. Divide that out, we get 4.49 pascals. All right, so the next thing we need to do is to look at how the hydraulic process is used, and this is amazing stuff here, if I don't say so myself. We have a car lift that is worked by having a cylinder in one place, creating a force on that pushes the force, the pressure over to the gigantic lift to lift up very heavy objects. So a lift that has a 10 centimeter diameter is connected to a cylinder of a diameter of 150 centimeters. 150 centimeters is just about 2.5 feet. If the small cylinder has 1.50 atmospheres above atmospheric pressure applied to it, how much force is available to the large cylinder? So we're going to use the Pascal's principle here, F1 over A1 equals F2 over A2. The first force is the 1.5 atmospheres plus the additional 1 atmosphere already being applied to it. So that's a total of 2.5 atmospheres. This then, we have to take the diameter and change it to the radius, change the diameter to meters, take half of that for the radius, which we've done a bajillion times. The area for a circle, as you know, is pi r squared, so that gives us 7.85 times 10 to the negative 3 square meters. The first pressure then is the first force, which is 2.5 atmospheres times 10 to the 5th pascals over atmospheres. Because pascals is the SI unit for pressure, we have to do that. Then we go ahead and plug it into this formula right here, solve for F1. The area we said is 7.85 times 10 to the negative 3 square meters, and we get 1,960 newtons. So that's our F1. Now we go back to F1 over A1 equals F2 over A2. And now we have to figure out the area of the circle. If it has 150 centimeters for diameter, that becomes 1.50 meters, which is, so I said 2.5 feet, that's more like 4.5 feet, my bad. So this is a monster lift. And this is the radius then is 0.750 meters. Area of the circle then is 1.77 square meters. Now we plug that into our proportion, get 1960 over 7.85 times 10 to the negative third was our first proportion. That pressure is going to be equal to the other side, so this is why these two sides are very important. When you change the size of the area, that's going to change the size of force. It's a direct relationship. and that turns out to be 4.42 times 10 to the 5th newtons. Big time stuff. Okay, so now you see the types of problems you're going to see in the practice problems. Go ahead and get to it. Have fun!